In the meantime, I suppose I better actually talk about some computer science for a change. The reason I'm showing you this, this stuff, it's not entirely irrelevant, but mostly I'm trying to amuse myself while I give my least favorite lecture of the term, which is about operating systems. I mean, everybody's got one. I mean, all of the machines that we use and the phones that we have operating systems. I'll give you your pen back. That's how bored I am. Yeah. So what do operating systems do for you? You know, lots of our machines allow multiple users to use them. So operating systems remember all the different accounts on them and allow individual users to log in. And if you're lucky, they remember individual users' settings. They'll also manage all the files on your computer system, and that's quite an important thing to do if you're into boring things being important. They might remember that some files are important for the system, whereas some files are important to individual applications, and then some files are the property of you as individual users. I mean, that's the point of operating systems, by the way, is to be boring, and it's actually a remarkably difficult thing to do, unless you're a lecturer at 1 o'clock in the afternoon on a Monday, in which case it's remarkably easy. So yeah, operating systems allow you, for example, to decide which programs you would like to run, and they enable you to interact with those individual programs. They allow you to delete your files by accident because they're not your mum. And what else do? They manage all sorts of stuff like, you know, does your computer have an internet connection that would allow you to find something more interesting to watch on the internet than listening to this lecture. You all sort of get the general idea of what operating systems do for you as a user of a computer system, and you have done for years. And you know, why is this still on the syllabus? God, I'm so bored. Tell you what, let's find out what happens next in the story of Mr. and Mrs. Meadow. So yes, so the detective follows Mr. Meadows, and then this happens.
Just a good night's sleep, that's all.
Any particular time in the morning?
Well, not so early.
He's checked into a bed and breakfast.
Perfect.
The breakfast is in there, and 10 o'clock is the absolute limit.
That's what they all say. Mostly travellers, I suppose.
Mostly, yes. Good night.
Yeah.
She runs the bed and breakfast.
Best breakfast I've had for years.
Good.
My compliments to the chef.
Compliments gratefully received.
Oh, you?
Bacon and eggs aren't that difficult.
Bacon and eggs and bacon and eggs. Staff must be a bit of a problem these days.
I don't need any.
You do it all yourself?
I'm one of those irritating people who organises things.
I can see that.
Flattery or insult?
A simple observation. Delicious honey.
Yes, it's from the hives.
You keep bees?
And I grow the vegetables and the fruit.
All yourself?
Terrible for the male ego, isn't it?
What can you do in your spare time? Build tractors?
I paint. I also make bees. I might even try and sell you some.
You know something? You might even succeed.
I'm up, man.
Oh, what time tonight?
Well, I'm not sure. I'm going to the Stevens place.
Ties it straight. Come
Get
here.
away.
Here, there.
Got your present.
Oh, surprise, surprise.
I forgot to give it to you last night. I had something on my mind. Good morning.
Good morning.
Detective has noticed that something is going on. Anyway, I suppose I should talk about operating systems a bit more now that my spirits have been restored by 1970s television. So let's think about what operating systems do for applications. Because they're not just there for you, they're there for the software that you run. So, for example, whenever you whenever you click with a mouse or something, do you think an applications program has to compute whether that click is for that application or for something else? No, that's done by the operating system. The operating system detects the mouse click and figures out which process, which of the things currently running on the system ought to pay attention to that mouse click. Same thing happens with things like keystrokes. You press when you press a key on the keyboard and some program is currently running. Do you think that your program has to be listening out for whether a key is being pressed like right now? I mean, when you write programs in Java, are you constantly issuing instructions to check whether somebody's pressed a key on the keyboard? And yet somehow while you type, if you type while a program is running, that somehow works. Well, how on earth is that happening? Well, the reason it's happening is that every time you press a key on the keyboard, that interrupts the program that you're currently running, and the operating system puts that keystroke somewhere for later use, and then your program resumes. You don't have to think about it when you're writing an application program. There are so many things that need to be managed for a program, for an application to get on and do its own business. Like, if you're using a system that's got like windowing, like this system's got my Twitter client and my Finder window and my QuickTime windows, do you think the person who implemented that Twitter client needs to ask needs to consider like whether part of my Twitter window is behind some other window in order to figure out what to display? I mean, that's not that program's problem. Whose problem is it? It's the operating system's problem. So operating systems programming, I mean, operating systems are amazing when it comes to letting programmers get on with writing applications that live in their own bubble. You should think about it's just astonishing when you're writing an application what you don't have to think about. And yet you can run a bunch of applications at the same time on a computer, and their display shows up in their window, their mouse clicks get through to the right place, their keystrokes get through. And there's something else that operating systems do which is really clever, which is that they pretend to every application that there is basically an infinite amount of available memory. Now you know that's not true, but from the point of view of an application says to the operating system, please may I have more memory, and what the operating system replies is yes. And it pretty much always says yes. It doesn't matter whether there is any more memory or not. It says yes, here's some more memory. What happens is that the operating system uses your hard disk as a place to keep lumps of memory that aren't very active at the moment. So it pretends to an application like there's a whole pile of memory available to it, and then anytime the application wants to access that memory, it ensures that the chunk of memory it wants to access is actually in the computer's memory. And if it has to fetch that chunk of memory off the disk and store something else on the disk to get out of the way, it will do that. And you may notice that when you have a bunch of applications going that are all memory intensive, things slow down and your hard disk starts getting really active, because that's the operating system juggling desperately with the memory it has available trying to make sure that still, whichever memory your application wants to access is available just when it's needed. So that's, operating systems are there to allow applications to live in their own little bubble, to access all sorts of system services, input-output devices, network, the file system, and most importantly, memory, without really having to think about exactly what's going on. So they're marvelous for what they allow us not to think about. With that in mind, let's see what happens when the crunch comes for Mr. Meadows.
You can take it just before you go back on Sunday.
What's the damage?
Oh, we'll settle up later.
Oh, you know me, Mrs. M. I'd have to keep things neat and tidy now. How much? What's this then? You're following me?
That's right, Mr. Meadows. From Windsor to Northampton to Cheltenham. Or, putting it another way, from wife to wife to wife.
So, of course, we have a cup of tea.
Thanks.
What do you do at Christmas?
Christmas?
You got 3 families. How the hell do you manage Christmas?
Oh, well. Christmas Day with the youngest children, Christmas Eve with Adele, and Boxing Day with Connie.
And they accept that?
Yes.
Never ask questions?
No.
And why not?
Because they know that when I go away, it's because I've got to.
You must have a mind like a filing cabinet computer.
Yes, I suppose I might.
You never made a mistake.
You must have a mind like a computer, says the detective. And quite right, he does. Because our Mr. Meadows is performing the perfect analogue of an operating system. Indeed, he's quite some operator, as you've seen. I don't necessarily wish to approve or disapprove of his conduct morally, but what's going on is that there are essentially 3 applications processes, and he's pretending to each of them that they are the only process involved. That's the incredible power of being. That's what operating systems lets you do if you're an application programmer. Is you can program as if the computer is entirely yours, even though you know fine well the operating system is arranging for the computing resources to be shared between you and a bunch of other processes. That's to say, operating systems manage multiple things going on at once. This is the origin of the term multitasking. You may have heard of multitasking. It's like being able to cope with a bunch of different demands for completely different things, requiring different bits of your brain to be working all at once. And there's a well-known rumor that women are better at multitasking than men. And this rumor is a lie, which is told by men in order to be given less multitasking to do. We're all perfectly capable of it, And it's a sort of just a terrible privilege to be allowed to focus on one thing at once and just pretending that you're rubbish at it in order not to be made to do it kind of sucks, really. You know, let's all grin and bear it. You know, how does multitasking work in practice? Well, there are two models of multitasking. One is called cooperative multitasking, where each of the different tasks decides for itself when it needs some resource and when it is free, when it can let go. So in cooperative multitasking, a process will run for as long as it wants to run, and then whenever it says, I'm done for the time being, it lets go of the processor and somebody else can have a go. It's like Xavier and Yvonne sharing a game or sharing a computer last time around, or whenever it was, where each of them keeps going for as long as they want, and only when they say they're ready to pause does control pass to whatever else might be happening. Do you think that's likely to work for an operating system? Well, no, it's not. And when you write programs that run on an operating system, do you often find yourself putting in a bit of code saying, well, I'm done for the time being, let somebody else have a go? No, you don't. So if we relied on cooperative multitasking, we'd be pretty royally stuffed. So how does it actually work? Well, it works by what's called preemptive multitasking. So that's where, instead of the applications deciding that they're done for now, the operating system decides how much time to give each application. So usually what will happen is that the operating system will set a timer counting down, let one process run. When that timer runs out, execution will be interrupted. The operating system will take the current state of the application that is running and store it carefully away so that that application can be resumed, and then another application will be restored into operation. So the operating system has to be, apart from anything else, a master of cryogenics. It has to be able to take a currently running program, stop it at any moment, and put it into suspended animation in such a way that it can be restored later. So that's why even on systems, I mean, these days systems have lots of processor cores and can do many things at once. But even when we had single core processors that could only do one thing at once, we still have multitasking operating systems, which would use this preemptive system to give the different applications very short time slices, so they were all taking turns. And it's just incredible to think that that's what's going on, and you as an applications programmer never see any of it. So that you've got that issue with how do applications share the resources of the system, including compute time on the processor. It's the operating system which is making sure that time is chopped up and shared out between the individual applications. And as Mr. Meadows says, it's because when I go away, they know it's because I've got to. The processors, they get their time slices, and they don't ask questions. I suppose you want to know what happens in the end. I haven't got the video clip for that, but I'll tell you. So the photograph, it turns out, is not of his other woman. It's of his daughter by the oldest wife. The detective tells young Mrs. Meadows this fact, and he confesses that he has been married before, and that he has a daughter, he doesn't say that he's still married to the mother of the daughter, or anyone else for that matter, and life goes on as normal. Yeah, so that's the kind of 1970s morality that this program specialized in. Messy little situations. There were never any murder. They couldn't afford to murder. I mean, for goodness sake, they could just about afford dialogue. Anyway, so not to make any particular judgment, but we can perhaps be less moralistic about, or perhaps we shouldn't be moralistic about this situation, except for the dishonesty involved. That's always problematic. But in the case of operating systems managing applications, then to some extent the dishonesty is just as well. I mean, you wouldn't like me going on about what I'm setting CS410 for their homework, would you? I try and manage my classes as if you're the only class I have. There we are. Of course, this multitasking business has all got more difficult now that Multicore has arrived. Now that we actually do have multiple processor cores that don't merely take turns to run programs, but actually run different programs at the same time. So the operating system's task has got a whole bunch harder. So the idea is that there are a bunch of different tasks to be run, and those tasks are often called threads. And it's the operating system's job to map the threads which have to be executed to the cores that are available to run them. So if one thread, and that can be done by sharing time out in the way that I described, but it can also be done on the basis that maybe one thread is blocked until some data comes from the network, so maybe that thread doesn't need any processor until the data arrives, so another thread can be swapped in. And then you can imagine, because the computer only has still one main memory, that the business of making sure that the appropriate stuff is actually in the physical machine memory for each of the threads that's currently running is a pretty tricky business. It gets worse, of course, because quite a lot of programming languages these days try to enable you to exploit concurrency features. And they allow you to say, oh, well, here are 1 million different things that can all be done at the same time. And there's only like 4 cores on the computer. So how does that work? So that means the programming language has its own notion of thread that's separate from the operating system's notion of thread. And these are called lightweight or green threads. So there might be 1 million green threads working together to compute some enormous calculation that your program wants to do. And what will happen is that the runtime system for that programming language will ask for exactly the number of threads that there are processors on the computer. So there'll be one operating system thread for each core, but 1 million different tasks to do. And then the programming language's runtime system will act locally like an operating system, dividing the 1 million tasks up between the one operating system thread it's got for each core. So in fact we have multiple layers of operating systems built into the systems we use today. But there's another piece of misery ahead associated with threads, which is especially if you've got a program that's trying to do a big calculation, and we kind of split it up into 1 million tasks that are all running at the same time. Well, maybe they're completely independent, or maybe they need to communicate with each other somehow. So how on earth does that happen? Well, if you're really lucky, you're in a situation where there's no attempt for two separate processes to use the same block of memory. So that processes can send each other messages, but they're not trying to occupy the same patch. So inter-process communication only by message passing. That's terribly lucky if you work at that level. But for a lot of the time, you don't get anywhere near that level. For example, if you're programming in Java like you do, you won't get anywhere near that level. You need to use a good programming language, not the ones we teach you. Well, not the ones we teach you in first year anyway. Some of us will teach you better programming languages later, don't worry. Yeah, so if you've got this sort of message passing situation, all is lovely, but how can a message passing situation possibly work? I mean, that's hiding some reality that's going on. In reality, what's going on is that we've got a von Neumann architecture. The machine has one main memory, and to some extent, that is shared by all the applications that are currently running. The operating system does a pretty good job of fencing off between applications the memory that is available. Have you ever encountered a segmentation fault as a thing? If you're lucky if you haven't. Segmentation fault is an operating system error. It means that one application has tried to access memory that belongs to another. And usually, instead of that just happening, the operating system causes the program to crash. And this is just as well because it would create massive security holes if it was possible for one application to read memory that belonged to another. But within an application, if you've got different sorts of memory accesses happening, and you've got the sharing of memory, then there are other things that can go wrong. Let me write some programs. Right. Let's think about being a bank. Okay. So once a month, the bank might have to run a program like this. Let's say it's the end of the month, right? And I'm getting paid. So there might be a program which is something like this: straff balance equals straff balance minus how much shall I pretend I get paid? Wishful thinking. Corner balance equals corner balance plus. Actually, it's more complicated than that, and I do pay tax. But yeah, that might be one program that the bank has to run, is to move 10 grand from the university's balance to my balance. But there's another program that has to run at the end of the month, which is my monthly trade union subscription. So that will look like UCU balance equals UCU balance plus 30. Actually, it's cheaper than that. Well worth it. And Connor balance equals Connor balance minus 30. Right? Everyone recognize these as sort of things that might happen? Doing 2 assignments in a row. Okay. Well, so first of all, we can think about what's going on in these 2 programs. So these programs, you can see there are 2 assignments, each of which is separated by a semicolon. Right. So a semicolon always tells you, do this, then do that. So we're going to do the first assignment, then we're going to do the second assignment. You're used to that, right? You've seen a semicolon by this stage. Okay? And then an assignment, what happens is that we compute the value of the expression on the right, and then we store it in the memory location indicated by the variable on the left. If you wanted to translate it into tiny, then unfortunately 10,000 isn't going to fit. But this is like, we load the contents of strath balance into the accumulator, and then we probably do some subtraction, and then we store the result back in strath balance, and so it goes. So if you look at what process A is doing, it's going to read strath balance, and then it's going to write strath balance with the new balance. And then it's going to do the next thing, which involves reading my balance, which is terrible today, and it's going to write back to my balance. Similarly, the memory accesses that are being done by program B are to read the union's balance, and then write the union's balance, then read my balance, and then write my balance. Okay, now let's see what happens. Let's suppose that at the start of this situation, my balance is, let's say I'm quite overdrawn, and the uni's balance is, let's say the uni has £1 million, if only that were true. And let's suppose that the union has 5,000. Okay, and we run these programs. What's my balance going to be at the end? Well, if we're lucky, I'll get paid 10 grand, so I'll go up to 7 grand, and then I'll go down to 6,970. The university will be 10 grand poorer, so that means it will have 990,000, and the union will have an extra 30 quid. That's what would happen if A ran and then B ran. But what would happen if A and B ran at the same time? I mean, one thing that could happen is, well, we know something. We know that my pay is definitely going to come out of the uni's bank account. And we know that my union subscription is definitely going to be paid to the union. But what might happen to my bank balance? Well, suppose, as it happens, program A, transaction A and transaction B, both do their 2 reads at the same time. Then they'll both read a balance of -3 grand. And then maybe program A writes, adds its 10,000 and writes that my balance is now 7 grand. And then program B computes that my balance ought to be -3,030, and then it writes that my balance is -3,030. That could happen. If the order of events is maybe this happens first, this happens second. Our only guarantee is that these things happen in order, and that these things happen in order. So maybe this happens next, and this happens after that, and then maybe this happens, and this happens, and then this happens, and then this happens. If that's the case, no such luck. My balance is minus 3,030. Ah, it's the shut up music, which may be familiar. So yes, there's a danger if we just allow these programs to run concurrently, sharing the same memory, that simply because, you know, if my salary arrives at the same time as my union subscription gets paid, that I might not get paid at all. There is, of course, also the danger that the two rights might happen in the other way around, in which case I might get 1 month free membership of the union. But you should understand, I mean, by and large, whilst banks process gazillions of transactions simultaneously all the time, this sort of stuff doesn't go wrong terribly often. So, what could possibly be going on to stop this kind of terrible, ghastly chaos of concurrent transactions sharing the same memory, not just stomping over each other and corrupting data massively? Well, for that, I'm afraid, you must wait until Friday's lecture. 1 minute papers in the box, please.